All right, so here we are, section 4.4, exponential and logarithmic equations. So now we're going to take what we learned in the previous sections, 4.1, 4.2, 4.3, and now we're going to put it all together, and we're going to use that information that we learned to solve these types of equations, exponential and logarithmic. So we're going to start with solving exponential equations. There's a couple of different ways that we could approach these. The first way is by expressing each side as a power of the same base. So what does that mean? Well, if I have some base to the m power, and I know that's equal to some base b to the n power, see how the bases are the same? Then in order for these two statements to be equivalent, the powers must be equal. M must equal m. So if that's the case, then if we're able to rewrite the equation in that form, then we could set the exponents equal to each other and then solve for the variable. So let's look at an example, but it's not always going to be possible to solve this way. If it's not, we're going to have other methods. But let's just look at the cases where it is. So look at A, we have 3 to the x is equal to 81, and we want to solve for x. So in other words, what would I have to raise 3 to in order to get 81? This we could do in our head, but I want you to see that if we can rewrite both sides of the equation in the same base, then we could set the powers equal to one another. So I'm looking at 3, right? That's the base on the left-hand side. 81 is the base on the right-hand side. And I'm thinking, how can I rewrite both sides so they have the same base? Well, I can write 3 to some power, and that's going to give me 81. What power can we raise 3 to in order to get 81? It's going to be to the fourth. So I can rewrite 3 to the x as being equal to 3 to the fourth. Because like I just said, 3 to the fourth power is 81. But now I have both sides of the equation written in the same base. So in order for these two statements to be the same, then the exponents must be the same, right? So then that means that x is equal to 4, right? 3 to the fourth is equal to 81. And you can check that on the calculator. So let's use the same idea for this next equation. In B, we have 2 to the 2x minus 1 power is equal to 32. So I'm thinking, all right, I see 32 as the right-hand side of the equation, and I see 2 as the base of the left-hand side of the equation. And I'm thinking I can rewrite 32 using the same base as 2. 2 to the fifth is 32. So what if I rewrite this as 2 to the 2x minus 1 is equal to 2 to the fifth? Because 2 to the fifth is 32. But now I have both sides written in the same base, which means that the exponents are going to be equal, right? So this means that 2x minus 1 is equal to 5. Now we could solve for x. So we're going to get 2x equals 6. If I divide both sides by 2, I'm going to get x is equal to 3. And always check your answer. If you go back to the original and plug in 3, we're going to get 2 to the 2 times 3 minus 1. 2 times 3 is 6. 6 minus 1 is 5. So on the left-hand side, we get 2 to the fifth. And 2 to the fifth is 32. So that checks out. So again, just in the essence of time, I'm not going to check every single one of these, but I expect that when you're doing your homework and you're working on, the work at home on your own, you're going to check your answers. So let's look at the next one. So we have 5 to the 3x minus 6 is equal to 125. So I see a 5, I see a 125, and I'm thinking I could rewrite this 125 with a base of 5. That's going to be 5 to the third. So this is going to be 5 to the 3x minus 6 is equal to 5 to the third power. Now I could set my exponents equal to one another. So I'm going to have 3x minus 6 is equal to 3. I'm going to add 6 to both sides. and I'm going to get 3x equals 9. Divide both sides by 3, and I'm going to get 9 divided by 3, which is 3. So x is equal to 3. And let's do one more. So for D, I have 8 to the x plus 2 power is equal to 4 to the x minus 3 power, and we want to solve for x. I'm going to try to do what we did for the previous ones, but I'm thinking, how can I rewrite 8 and 4 so that they have the same base? I can't rewrite 8 in base 4. So I'm thinking, can I write both of them over, but in a common base? And I'm thinking 2, right? Because 2 to the third is 8. So if I rewrite 8 as 2 to the third, right, to the x plus 2, and set that equal to 4, I could write as 2 squared, right? 2 squared is 4, same thing, to the x minus 3. And now what I could do is use the rules that I learned in P2. Remember the first days of class of the semester, the first videos, we were using the power rule for exponents. Whenever I raise an exponent to an exponent, we use our power rule, right? So this is going to be 2 to the 3x plus 6 is equal to 2. And now I'm going to distribute the 2 to the x minus 3. So to the 2x minus 6. Now I have an equation where both sides have the same base of 2. So now in order to solve for x, I could set the exponents equal to one another. So I'm going to get 3x plus 6 equals 2x minus 6. So I'm going to subtract 2x from both sides, and then I'll subtract 6 from both sides. So 3x minus 2x is going to be 1x. And that's going to equal negative 6 minus 6, which is negative 12. So x is equal to negative 12 in this instance. We can also use logs to solve exponential equations. And I think this is the more common method because a lot of times, like I said earlier, it's not going to be feasible to rewrite both sides of the equation using the same base. So if we can't solve it the way we did above, then we could use logs to solve exponential equations. So the first thing we would do is isolate the exponential expression, and then we would take the common log on both sides of the equation for base 10. Remember, common log is base 10. Or we could take the natural log on both sides for bases other than 10. So if we had base e, that's a nice time to take the natural log, and I'll show you. Then we could simplify using one of the following properties. So the natural log of b to the x, if I use my power rule, remember, is x times the natural log of b. Or if I have the natural log of e to the x, I could use my power rule and write that as x times the natural log of e, which is just going to be equal to 1. And the log of 10 to the x is also going to be equal to x. And that's because the log of 10 is equal to 1. And I'll talk about that in a minute when we get there. And then we're able to solve for the variable. So look at example 2. We want to solve the following equations. So you see, I'm going to make this a little bit bigger. It's not going to be feasible to rewrite 134 as base 5 and set the exponents equal to each other like we did in the previous example. So I'm going to use log. So what I'm going to do is I'm going to take the common log of both sides. So if I take the log of 5 to the x, then I have to take the log of 134, right? Whatever I do to one side, I have to do to the other side. The reason that I'm doing this is because we're trying to solve for x, but x is stuck in the exponent. We want to free x, right? We want to get x alone so that we could solve for it. But if I take the log of 5 to the x, now I could use my power rule and bring the x, right, the exponent to the front by multiplication. So I'm going to get x times the log of 5. And that's going to equal the log of 134. And now to get x by itself, so now I could solve for x, right? So this is x times the log of 5. So if I divide by the log of 5 on both sides, now I have x is equal to the log of 134 divided by the log of 5. And this would be my exact answer. This is ugly. If we plug this in the calculator, so I just want to show you, if you needed to get an approximate answer, we could plug it into the calculator and round. So if we plug this into the calculator, and I'll do it just for this one. So we want to take the log of 134 divided by the log of 5. We get about 3.04. So if I needed an approximate answer, x is approximately 3.04. Most of the time, we want to leave our answers in exact form. When would we use approximate form? Well, if we're doing a word problem, usually when we're looking at an application question, it's nice to get an approximate answer because then we could write it in terms of the units, that the problem is referencing. But let's check this. I want you to see that if x is about 3.04, then 5 to the 3.04 should give us about 134, right? Because that's what we just solved. So let's go to the calculator and take 5 and raise it to the 3.04. You see how we get 133.3? There's a little bit of rounding error because I rounded, right? That 3.04 is really 3.043198,972. So look, if we go out a little bit further, if I do 5 raised to the 3.043198,972, we're going to get closer to 134. You see how much closer? Because there's not as much rounding error. That's why we like to leave our answers in exact form. So let's look at another one. So for B, we have 10 to the x equals 8,000. So we're in base 10, so I'm going to take the common log. So I'm going to take the log of both sides. So we're going to have the log of 10 to the x equals the log of 8,000. I'm going to use my power property, right? So this is going to be x times the log of 10 is equal to the log of 8,000. And the log of 10 is equal to 1. Because remember, we're in base 10, right? 10 to the 1 is equal to 10. So log 10, this log 10 right here that I'm highlighting, but this is getting a little wacky, is really equal to 1. So this is really just x is equal to the log of 8,000. And again, we could put the approximate answer into the calculator, but I want to leave it in exact form. So this would be my exact answer. X equals the log of 8,000. So let's look at the next one. So part C, we have 5 times e to the x equals 23. So again, we're trying to solve for x, right? The only term that contains x is the e to the x. This 5 is just attached by multiplication. So if we go back to the steps, you want to isolate the exponential expression, get it by itself. So let's get e to the x isolated. So we're going to divide both sides of the equation by 5. So now I have e to the x equals 23 divided by 5. Now that I have the exponential expression isolated, now I could take the log of both sides. So we could bring x down to the front by multiplication. But since now my base is e, you see how my base is e? I would use the natural log. Because remember, the natural log, when I press ln on the calculator, the base is e. And you'll see why this is going to be nice. So look, let's take the natural log of both sides. So the natural log of e to the x is going to be equal to the natural log of 23 over 5. Let's use our power rule. So this is going to be x times the natural log of e is equal to the natural log of 23 over 5. And the natural log of e, which I just highlighted, and I'll write it up here. So the natural log of e is equal to 1. Because remember, this is base e. So e to the 1 is equal to e. So whenever we have the natural log of e, that's always going to be equal to 1. And you could type that in the calculator. Type in ln of e. You're going to get 1. So this is just x times 1, which is x. So x is equal to the natural log of 23 over 5. Let me show you how to check this. Let's just check one more so I know that you guys are comfortable checking. So the original is 5 times e to the x should give us 23. So let's replace x with the natural log of 23 over 5, right? That's what we just got. So we got x to be equal to the natural log of 23 over 5, and we want to plug that into the calculator. So we want to type in 5 times e raised to the natural log of 23 over 5, right? And we should get 23. So let's check. So let's take 5. Now, if I pull up E, remember that's second and then the ln key, that's E to the, now I can plug in a power, right? So 5 times E raised to the, now for X, we got the natural log of 23 divided by 5. And we get 23, right? That checks out. So you could always check your answers to these. So let's look at the next one. So for D, we have 7 to the x plus 2 equals 410. So we want to free the exponent, right? Because right now x is tied up in the exponent. So I want to be able to use my power rule, but first I got to take the log of both sides. We're not in base E this time. So usually I only use the natural log ln if we're in base E. Any other base, I usually just use the log, the common log, log. Unless if you're doing the homework and the homework asks you to specifically use the natural log, then use it. Honestly, you could use either one. It doesn't matter. So I'm going to take the log of both sides. So we're going to have the log of 7 to the x plus 2 equals the log of 410. And now I'm going to use my power rule. So I'm going to bring the x plus 2 to the front by multiplication. So x plus 2 times the log of 7 is going to equal the log of 410. Now I have to distribute because we have a group here, right? So I'm going to take x times the log of 7 plus 2 times the log of 7 equals the log of 410. And we're trying to isolate x, right? This 2 times the log of 7 right here doesn't have an x term associated with it. So I'm going to bring it to the other side. So I'm going to subtract 2 times the log of 7 from both sides. So we're going to get x times the log of 7 is equal to the log of 410 minus 2 times the log of 7. And now to get x by itself, I'm going to divide both sides by the log of 7. Now I'm just going to have x on the left-hand side, and that's going to be equal to the log of 410 minus 2 times the log of 7 divided by the log of 7. And that would be my exact answer. And you could check your answer in the calculator. All right, so let's do the last one, part E. I'm going to go to the whiteboard for this one just because I'll have more room over there and I don't want to erase, what I have here. So we have 3 to the 2x minus 1 is equal to 7 to the x plus 1. So let's go over to the whiteboard. Okay, so we have 3 to the 2x minus 1 equals 7 to the x plus 1. So we're going to do the same thing. We're going to take the log of both sides. We're not in base E, so I'm not going to take the natural log. I'm just going to take the LOG. So let's take the log of 3 to the 2x minus 1 and set that equal to the log of 7 to the x plus 1. Now choose our power rule. So bring the powers to the front by multiplication. So I'm going to have 2x minus 1 equals, times the log of 3 is equal to x plus 1 times the log of 7. So now let's get rid of those groupings, right, by distributive property. So I'm going to multiply on the left-hand side. So I'm going to have 2x times log 3. Now distribute the negative 1, so minus log 3. That's going to equal, now distribute on the right-hand side. So x times the log of 7 plus 1 times the log of 7, which is log 7. This is just like solving a linear equation for x. Gather the x terms to one side, gather the constants to the other side. So what I'm going to do is I'm going to bring the x terms to the left. So I'm going to subtract x times the log of 7 from both sides. So, and then I'm going to add, let's just do this in one step, then I'm going to add log 3 to both sides. So on the left, I'm going to have my x terms. So I'm going to have 2x times the log of 3 minus x times the log of 7. And I forgot my g right there. That's going to equal the log of 7 plus the log of 3. So you see how I gathered my x terms to the left-hand side of the equation and I gathered my constants to the right-hand side of the equation. But remember, the goal is to solve for x. But I have two different x terms on the left-hand side. So what I'm going to do is let's factor out the x, right? Each one of these terms on the left has an x in common. Let's take it out. Let's factor it out. And we're going to be left with 2 times the log of 3 minus the log of 7 is equal to the log of 7 plus the log of 3. So all I did was factor out the x. Now, in order to get the x by itself, I can divide by the 2 times the log of 3 minus the log of 7. So my answer is going to be x is equal to the log of 7 plus the log of 3 divided by 2 times the log of 3 minus the log of 7. And that would be my exact answer. So that's how we solve exponential equations by taking the log of both sides. So I did 4 different examples. So, you could see different situations, different scenarios, different bases. All right, so let's just put a note over here. So this was done on the whiteboard. Okay. So now we're going to look at it from the other perspective. So now what if I have an equation that contains logs? So logarithmic equations, how do we solve those? Well, there's a few different ways to solve these as well. It just kind of depends on the form. So what form this takes on. So I can see here that, well, first of all, let's kind of just start with the step. So express the equation in the form log base b of m equal to c, which is some constant. Then we could use the definition of logs to rewrite the equation in exponent form. And then we're able to solve for the variable. And of course, you always want to check your answers. So let's look at the first example. Look at example 3. So example 3a, we already have the form log base b of m, where m is x minus 4, is equal to 3, which is like c, right? Rewrite this log statement as an exponent. And we practiced doing this in the previous sections. So in order to write log base 2 of x minus 4 equals 3 as an exponential equation, remember, take the base b, so take 2, raise it to the y, which is 3, and set it equal to m in this case, right? So x minus 4. And I'm sorry, that shouldn't be y, that should be 3. Right? Normally so remember, when I taught you about how to go from logarithmic form to exponential, so remember we had log base b of x is equal to y. And we said that's the same thing as b to the y equals x, right? And that's all I did over here. So 2 to the 3 equals x minus 4. And now I could easily solve for x, right? I could get x by itself by adding 4 to both sides. So I'm going to get x is equal to 2 to the 3rd plus 4. 2 to the 3rd is 8. So we get 8 plus 4, which is 12. And that's going to be equal to x. And of course, you always want to check your answers. You want to plug in 12 for x. 12 minus 4 is 8. And 2 to the third gives us 8, right? So that checks out. So let's look at the next one. We want to isolate the log expression. We want to get it alone on one side of the equation. We have this 4 in front by multiplication, right? So let's just divide out first. So we're going to get the natural log of 3x is equal to 8 divided by 4, which is 2. Now, let's rewrite this expression in exponent form. So remember, when we're talking natural log, the base is e. So I'm going to rewrite this as e to the second power equals 3 times x. And now I could solve for x, right, by dividing by 3. So x is equal to e to the second power divided by 3. And that would be my exact answer. If you were to plug that in the calculator, you're going to get a decimal answer. So let's look at C. We have log x plus the log of x minus 3 is equal to 1. This is a little bit different now because I have 2 log expressions in my equation. The 2 that we did previously just had 1. But let's think back to the previous section that we covered and our properties for logs. Remember, whenever I have the sum of 2 logs that have the same base, we can rewrite it as a product, right? This is the same thing as the log of x times x minus 3. And that's equal to 1. So remember, and I'll put that up here. Remember, the log of m times n is equal to the log of m plus the log of n. And x times x minus 3, I could just multiply that out, right? So this is the log of x squared minus 3x equals 1. And now let's rewrite this log as an exponential expression. Log is base 10, right? So there's a 10 here. So 10 to the first power is equal to x squared minus 3x. And 10 to the 1 is just 10, right? So 10 equals x squared minus 3x. And you should recognize this type of equation. This is quadratic, right? And the way we solve a quadratic is set it equal to 0 and see if you could factor it. Otherwise, we would have to use the quadratic formula. So let's subtract 10. And we're going to get 0 equals x squared minus 3x minus 10. Are there 2 numbers that multiply to negative 10 and add to negative 3? Right, because we want to factor this. And it's going to be negative 5 and positive 2, right? Negative 5 times 2 is negative 10. Negative 5 plus 2 is negative 3. So now the way we solve this is set each factor equal to 0, right? So either x minus 5 equals 0 or x plus 2 equals 0. So we're going to get x equals 5 or x equals negative 2. Now, we have to think about our domain. And we did this in the previous section when we looked at the graph of log x. The domain was all values of x such that x is greater than 0. So x has to be greater than 0 when we're talking log x. So if I were to, I'm thinking this x equals -2 is not gonna be good, right? Look, let's check x equals 5. If x was equal to 5, then we would have the log of 5 plus the log of 5 minus 3, which is the log of 2. That should equal 1. And let's do log 5 plus log 2. And we get 1. You see how that checks out? But look what happens when I try to check x equals -2. If I were to try to check -2, then I would get the log of -2 plus the log of -2 minus 3, which is -5. -2 and -5 are not part of the domain for the logarithmic function. Look what's going to happen just when I try to take the log of -2. If I try to type in log of -2, the calculator is going to tell me that that's not a real answer. So we have to reject that possible solution because it's not part of the domain. So my solution is x equals 5. So you only have one solution in this case. And let's do one more. We'll do it on the whiteboard. So let's we'll do work on whiteboard. All right, so for this one, we have log base 2 of x plus 2 minus log base 2 of x minus 5, and that should give us 3. All right, so let's go over to the whiteboard. All right, so we have log base 2 of x plus 2 minus log base 2 of x minus 5, and that should equal 3. So let's rewrite this as a single log. I see we have subtraction, so I'm gonna use my quotient rule, remember from the previous lecture. So I'm gonna rewrite this as log base 2 of x plus 2 divided by x minus 5. And that's gonna equal 3. So remember, if I have log of m divided by n, that's equal to log m minus the log of n. So I'm just using that rule. So now let's rewrite this single log as an exponent or an exponential expression, right? So we're going to take base 2 to the third power. That should equal x plus 2 over x minus 5. And 2 to the third is 8. So we get 8 equals x plus 2 over x minus 5. And this is just a proportion. We could solve this by cross multiplying. So I'm going to get 1 times x plus 2, which is x plus 2. Set that equal to the other cross product. So 8 times x minus 5. So we're going to get x plus 2 equals 8x minus 40. So I'm going to add 40 to both sides. and I'm going to subtract x from both sides. So I'm bringing the x terms to the right, the constants to the left. So I'm going to get 42 is equal to 7x. And to solve for x, now I could divide by 7. 42 divided by 7 is 6. So we get x is equal to 6. And again, you could go back to the original and check your answer. All right, so let's move on. So there's one other property that we could use to solve logarithmic equations. It's called the one-to-one property of logs. So if I have log base b of m, and that's equal to log base b of n, so you see how both bases are the same, then that means that m must be equal to n in order for both sides of the equation to be true. So for example, if I have log base 2 of 7, and that's equal to log base 2 of x, what does x have to be? Well, it has to be 7, right? That's the only way that the left-hand side is going to be the same as the right-hand side, right? So this means that 7 would have to be equal to x. So we could use that property as well. So how do I know when to use that property or when to use the previous properties that we were using, right? Where we take the log of both sides, or if I combine log statements, right? So it's like, how do I know what properties I'm supposed to use? So this is the way I approach them. Like, look at example 4. I have a single log and it's equal to some constant. So in this case, I would just use the exponent form. I would just rewrite this as an exponent. So natural log means we have base e. So I'm going to take my base, raise it to my exponent, which is 2, and set that equal to x minus 3. Now you see how easy it is to get x by itself. So I'm going to add 3 to both sides, and I'm going to get x is equal to e squared plus 3. But if we look at the example in B, now you see how I have 2 log expressions, but they're on either side of the equal sign. But they have the same base, right? They're both base 10. It's just not written because that's assumed, right? But if they're both written with the same base, then that means that whatever this expression is, right, the 2x plus 4, it has to equal this other expression, which is x squared minus 4. So that's this property that I was talking about earlier. So we can set 2x plus 4 equal to x squared minus 4. They have to be equal, right? Because that's the only way that both sides of the equation, both sides of this equation are going to be exactly the same. They have to equal one another. So we set them equal to each other, right? And now this is a quadratic because I have an x squared term. So let's set the quadratic equal to 0. So I'm going to subtract 2x from both sides, and I'm going to subtract 4 from both sides. And let me just move this over a little bit. So I'm going to have 0 is equal to x squared minus 2x minus 8, right? Because we have a -4 combined with another -4. So now I need to think of two numbers because I want to solve this quadratic, right? But in order to do that, I'm going to try to factor. So 0 is going to be equal to, all right, two numbers that multiply to -8 but are going to add to -2 is going to be -4 and +2. So set each factor equal to 0. So x minus 4 equals 0 or x plus 2 equals 0. So I'm going to get x equals 4 or x equals -2. So those are my two possible solutions. But let's check them. Let's see if, which ones make sense. So let's check x equals 4. If x was equal to 4, then I would have the log of 2 times 4, right, which is 8. 8 plus 4 is 12. So I would have the log of 12. And that would be equal to the log now of x squared, but we're testing x equals 4, right? So 4 squared is 16. 16 minus 4 is 12. And log 12 is equal to log 12, right? So 4 checks out. Now let's check x equals -2. If x was equal to -2, then I would have the log of 2 times -2 would be -4. -4 plus 4 is 0. So I would have the log of 0. This is already a problem because x has to be greater than 0. But look what happens when we plug in on the other side. So -2. If I were to plug in x equals -2, -2 squared is 4. 4 minus 4 is 0, right? But think about what I just said. So let's go to the calculator. And when we try to type in the log of 0, we're going to get an error message because remember, it goes back to the domain. Remember the domain of the log function. X has to be greater than 0. It can't be equal to 0. So we have to reject the -2. It doesn't make any sense. So my solution is x is equal to 4. So I can't stress enough how important it is, to check your answers. All right, so we're going to wrap up with word problems. So now let's apply what we've been doing, solving the exponential and logarithmic equations, but in the sense of a word problem. So I have 3 examples, and then we'll wrap up. So example 5 says the percentage of adult height attained by a girl who's x years old can be modeled by the function f of x equals 62 plus 35 times the log of x minus 4, where x represents the girl's age anywhere from 5 to 15, and f of x represents the percentage of her adult height. At what age has a girl attained 97% of her adult height? So we want to know at what age. Age is X, right? X represents the girl's age. And f of x, or y, represents the percentage of her adult height. We're being given the percentage of her adult height. So we're being told that the percentage of her adult height, f of x, is equal to 97%. We want to know at what age does that happen? So we know what y is, or f of x, right? The output, but we don't know what the input is. We don't know what x is, her age. So let's set f of x equal to 97. So we would have 97 equals 62 plus 35 times the log of x minus 4. So now I only have one unknown in this equation. It's x, right? And that's what we want to solve for, the age of a girl who's attained 97% of her adult height. So we set the equation equal to 97, and now we have to solve for x. And this is just what we were doing, in the similar questions above. So we have a log equation. We want to solve for x. We have a single log statement in there, right? There's only one log statement in there. So let's isolate it. Let's get it by itself. So let's subtract 62 from both sides. So we're going to get 35 equals 35 times the log of x minus 4. And remember, we're trying to isolate the log expression. So we want to get log x minus 4 by itself. So let's divide by 35. So 35 over 35 is 1. So we're going to get 1 equals the log of x minus 4. And remember, this is the same thing as 1 equals log base 10 of x minus 4. We just normally don't write the 10, right? It's assumed. But remember how we solve a log equation with a single log? Write it as an exponent. So this is the same thing as 10 to the first power equals x minus 4. All I did was rewrite it in exponent form. So remember, log base b of x equal to y, I can rewrite that as b to the y equals x, which is exactly what I did here. Now I'm able to solve for x, right? Add 4 to both sides. 10 to the 1 is just 10. 10 plus 4 is 14. So we get x is equal to 14. And we're talking years, right? So a 14-year-old has attained about 97% of her adult height based on this model. And that would be the solution. So 14 years old. So just another example of how to solve a log equation, but in terms of an application question. Let's look at example 6. So a cup of coffee is taken out of a microwave oven and placed in a room. The temperature T in degrees Fahrenheit of the coffee after T minutes is modeled by the function T equals 70 plus 130 times e to the negative 0.04855 T. After how many minutes will the temperature of the coffee reach 120 degrees Fahrenheit? So this function here, the T equals 70 plus 130 times e to the negative 0.04855 T, models the temperature of the coffee as a function of time, how much time it has gone by after it's taken out of the microwave. So lowercase t represents time in minutes after it's taken out of the microwave. And the capital T stands for temperature. So the temperature is capital T. And we're in degrees Fahrenheit. So after how many minutes will the temperature of the coffee reach 120 degrees Fahrenheit? So this is a value of capital T, right? The temperature. And we want to know after how long, after how many minutes, which is lowercase t. So if we set capital T equal to 120 degrees, right, that's going to equal 70 plus 130 times e to the negative 0.04855 T. Now I could solve for t, right? The only unknown that I have in this expression is lowercase t. And this is an exponential equation, right? Because it doesn't have logs in it, but it has an exponent statement. You see how we have e to the negative 0.04855 T. That's the exponential expression that we want to isolate. We want to bring everything else to the other side. We want to get that alone. This way we can take the log of both sides. So let's subtract 70 from both sides of the equation. So we're gonna have 120 minus 70, which is 50, equals 130 times e to the negative 0.04855t. And we want to isolate the exponent expression. The 130 is not part of that. It's just hanging around there by multiplication. So let's divide both sides by 130. So we're going to get 50 divided by 130 is equal to e to the negative 0.04855t. So remember what we were doing at the beginning of this lesson when we were solving exponent equations. If we were in base e, we were taking the natural log, right? Because then we're going to end up with the natural log of e, which is just 1, and it just makes the simplification process easier. So since we're in base e, I'm going to take the natural log of both sides. So I'm going to have the natural log of 50 over 130 is equal to the natural log of e to the negative 0.04855t. And now I could use my power property, right? So since I have a log with a expression raised to a power, I could write that in the front as multiplication. So we're going to have the natural log of 50 over 130 is equal to negative 0.04855t times the natural log of e. So all I did was bring that power to the front by multiplication. And remember, the natural log of e is equal to 1. So we have the natural log of 50 divided by 130 is equal to negative 0.04855t, because it's just being multiplied by 1, right? That natural log of e just is 1. And now how do we get t by itself? Well, we divide by negative 0.04855 on both sides. So t is equal to the natural log of 50 divided by 130 divided by negative 0.04855. And since this is an application question, let's plug this in the calculator to get an approximate answer. Because remember, we're solving for time. If we were to leave our answer like this, it looks weird, right? Because how do we interpret that as time? So let's plug it into the calculator. So let me share my screen. So we have the natural log. Let me quit out of here. So we have the natural log of 50 divided by 130 divided by negative 0.04855. And we get about 19.68. And 19.68 is about 20 minutes, which is about 20 minutes. So after about 20 minutes, the coffee reaches 120 degrees Fahrenheit. That's what we just calculated after we take it out of the microwave. And let's do one more. So example 7, this is modeling a population. So the function A equals 82.3 times e to the negative 0.004 times t models the population of Germany. We'll call the population amount A in millions, t years after 2010. So in which year will the population of Germany reach 79.1 million? So this equation is calculating population of Germany, which is A. But it depends on time, which is T, right? How many years after 2010? So the question is, so first of all, let's write down this model, right? So A is equal to 82.3 times e to the negative 0.004 t. So we want to know, when is the population of Germany going to be 79.1 million? So I'm asking for when A is going to be 79.1, right? Because that's the population amount. So let's set A equal to 79.1. That has to equal 82.3 times e to the negative 0.004 t. And we want to know, in what year will that happen? So we're solving for t, because t is the number of years after 2010. This is an exponential equation. So let's start by isolating the exponent expression, right? Here's my exponent expression with base e. It's e to the negative 0.004 t. So the first thing I'm going to do is isolate that expression. So let's divide by 82.3. So I'm going to have 79.1 divided by 82.3 is equal to e to the negative 0.004 t. Now that I isolated the exponent term, we're ready to take the log. But since we're in base e, I would take the natural log. So let's take the natural log of both sides. So we're going to take the natural log of 79.1 divided by 82.3. Set that equal to the natural log of e to the negative 0.004 t. Use your power property. So the natural log of 79.1 divided by 82.3 equals negative 0.004 t times the natural log of e, right? So we bring that power to the front by multiplication. And we know that the natural log of e is equal to 1. So we have the natural log of 79.1 divided by 82.3 is equal to negative 0.004 times t. And now we want to solve for t, right? We want to get t by itself. So I'm going to divide by negative 0.004 on both sides. So t is equal to the natural log of 79.1 divided by 82.3 divided by negative 0.004. And then that we could just plug into the calculator. So we're taking the natural log of 79.1 divided by 82.3, and we want to divide that by negative 0.004. All right, so in the calculator, let's type in natural log, and then in parentheses, we have 79.1 divided by 82.3. Make sure you close your parentheses. And then we divide by negative 0.004. And we get about 9.91. So T is 9.91. And remember what that represents. T represents the number of years after 2010. So this is 9 years after 2010. So that's the year 2019, right? If we take 2010 plus 9 years later, that's going to be 2019. So the population of Germany hit 79.1 million in 2019 based on this model. So this wraps up section 4.4. We're going to, end this with the word problems. And then we're going to be starting trig after this.